Hello, everybody, and welcome to cryptographic analysis of Delta Chat. This is work by Yuanming, Lenka, Mareková, and Kenneth Paterson. I am Matteo Scarlata, and I will be a proxy speaker for this talk. The authors couldn't make it. So what is Delta Chat? As you have heard, Delta Chat is this decentralized mail application based on email infrastructure. What this means is that they don't run their own delivery servers. You can just sign up into Delta Chat using an existing email account. So they will use the existing email to send messages. Why do we care about Delta Chat? Well, it's an interesting target, but it also engages with high-risk users. So according to their own report, they have users in Belarus, Russia, Ukraine, Iran, Taiwan, and Hong Kong. So it's important for us to check that their cryptography is sound. How is Delta Chat built? Well, let's start from the bottom. In the technology stack, we have at the lowest level the email infrastructure, which may or may not be secure, right? You have normal SMTP and IMAP, and hopefully SMTPs and IMAPs, so TLS secured version of this, but these are not end-to-end encrypted in any way. On top of SMTP and IMAP, we have a subset of OpenPGP. Now, I wish I could say that OpenPGP is our beloved standard for email encryption, but it's actually very complex. The standard spans several RFCs, and as Moxie Malin-Spike puts it, it's not very usable. The GNU-PG manual is over 16,000 words long. For comparison, Fahrenheit 451 is only 40K words. So since we don't want our Delta Chat user to have to read 16,000 words to use our messaging application, Delta Chat builds upon AutoCrypt. AutoCrypt is a layer that automatizes the key management of Delta Chat based on TOFU, trust on first use, and on gossiping mechanism. So like whenever you send a message to another user, you will attach the public key needed to verify the signature of this message so that like a lot of the overhead of PGP is gone. And all of this was already built, but on top of AutoCrypt, Delta Chat builds unverified chats. So this is just a simple wrapper to AutoCrypt where like you have an instant messaging interface to an email client. And then Secure Join. Secure Join is a protocol that helps verify the end-to-end integrity of the chats. So it allows you to verify by QR code scanning and by sending some messages between the user doing the scanning and the user being verified that you're actually talking with who you think you're talking. And this allows them to build at the top of this stack verified chats with end-to-end encryption guarantees. So what does verified chat actually looks like? Well, here we have Alice and Carol exchanging some messages. You will see Alice with her SMTP server and Carol with her SMTP server. Remember, this is a decentralized infrastructure, so every user has their own home server that the messages will be passing through. And a Delta Chat message will look something like this. Outside on the outer envelope, you will see the normal SMTP headers, and then inside you will see some other non-standard headers that are used by Delta Chat, like a group ID. And inside, like the inner header is all protected by PGP. Now, since Alice could have multiple devices, Alice will always also send messages to herself using the BCC feature of the emails so that the state is synchronized across all of Alice's device. So far, so good. It's very simple. Delta Chat also offers group chats. So let's take the example from before, but now we want to invite Bob to the group chat between Alice and Carol. In this case, Alice knows Bob's keys, Bob's public keys. It has verified them. But Carol doesn't know Bob's public key. So what Alice will do is send this message saying that she's adding Bob to the group. And then we'll also gossip the public key of Bob so that Carol can learn it. And then this message gets delivered to both Carol and Bob and Alice's other devices. So this is the starting point. The research of Lenka, Yuanming, and Kenneth is a deep dive on the cryptography of Delta Chat, looking at the security of all the different components in there. But this talk will focus on two attacks, the gossip key injection and the insecure join observer. Let's start with the gossip key injection attack. So you saw before when I showed you how Alice invited Bob to a secure group chat, Carol automatically learns and trusts the key of Bob through a gossip message. So let's take a second look at that. What actually happens under the hood is that Carol is maintaining a table with peers and their public keys. So when Carol receives this message from Alice, she will update this table saying that, oh, I received a gossip key. I received it in this moment today. And then since this gossip key is contained in a verified message, in a secure message from Alice, it will be immediately copied and trusted. And the problem with this mechanism is that there is some sort of race condition on the gossip time. So let's say that now I'm Mallory, and I want to take over Bob's identity. So I can send a message to Carol without pretending to be Alice, like just as Mallory. I will tell Carol, hi, Carol. And then I will include into my message a gossip key for Bob, which is not the real key of Bob. It's a key controlled by Mallory. And now Carol, upon receiving this message, will populate her table with the gossip key, which she believes is of Bob's, but it's actually of Mallory. And she will not copy this key to verified key because this message doesn't come from a trusted sender. But then later, when Alice actually tries to add Bob to a group, then Carol will receive a trusted message and will check in the table whether the gossip key is more recent or less recent than the one that she currently has. But since Mallory has set a date in the future for the gossip key that she had, so the date is arbitrary, it's unauthenticated in email, so Mallory can just pick date in the future, then Carol won't update the gossip key to match the new key sent by Alice, and she will actually just copy the wrong verified key, and therefore trusting Mallory's key. So this is a very powerful attack because this allows Mallory to effectively impersonate Bob in every action towards Carol. Our second attack is on the secure join mechanism. So we saw before this is the mechanism that allows users to verify each other by scanning QR codes. And how does this work in more detail? Well, Alice, when scanning Bob's key, Alice will send this confirmation message to herself and to Bob. This is needed because Alice may have multiple devices, but will only be scanning with one device. So maybe she uses her phone to scan the QR code, but then she wants her laptop to also trust Bob's key. And what can go wrong here is that there can be a confusion between protected email headers and unprotected ones. So the protected ones are the one inside the inner envelope protected by OpenBGP, and the unprotected one are just normal SMTP headers. So the SMTP server that Alice is using could send her a message with an autocrypt header with a fake key for Bob. And then if Alice replies to this message, she will send back like the current key, what she believes is the current key of Bob, in a protected header. Now, like the SMTP server can observe this message, which contains a protected header with Bob's gossip key, and add an unprotected secure join to it, and send it back to Alice. And now Alice will believe that this message is sent by herself, maybe from another client, and therefore accept this as Bob's verified key. This again allows the attacker, in this case an SMTP server, to impersonate Bob to Alice in all the ways, and maybe Alice could also be tricked into sending some protected information encrypted with a key that she thinks is of Bob, but actually is controlled by an attacker. These are not the only attacks that the research found on DeltaChat. There are actually several other attacks that allow to remove arbitrary group members, to forge multi-device synchronization messages, forge messages for key transfer between devices, then a denial of service attack based on a compression kind, and other attacks on DeltaChat's threat model. All of these attacks were disclosed to DeltaChat, and their response was very prompt. They fixed most of the attacks, and then they released like this message saying that they fixed in their version 1.44 release all the 20 issues identified by this research. What are a few takeaways of this security analysis? Well, vulnerabilities were found in DeltaChat, even if it passed several security audits. And this happened because what they were trying to do was actually underspecified or misspecified. So it was hard for other researchers to find these vulnerabilities. And in general, the use of OpenPGP and AutoCrypt was dangerous because they were using these building blocks in a non-standard way. And OpenPGP has also a lot of out-of-date crypto that should be, that could benefit from crypto from the crypto research proposal. So done with the main content, and I'm happy to take questions.